Good morning everyone. Today I'll be presenting a concept video on Introduction to Crystal Structures. This is a part of Applied Physics course. My name is Zavia Isra and my roll number is 24951A12C8. I am from Information Technology branch. Today we are going to be diving into crystalline structures and materials where atoms and molecules and ions are arranged in a highly ordered repeating 3D structure. This structure is what separates crystalline solid from amorphous ones like glass. Crystalline solids are backbone of material sciences, engineering and many technologies we use every day. Crystal lattice structure. At the heart of every crystalline solid is the crystal lattice. A unit cell is the smallest repeating unit of this lattice. By repeating the unit cell in space, the crystal structure is built. Some common types of lattice include simple cubic, body-centered cubic, face-centered cubic, hexagonal pack, there are 14 unique ways to arrange the structure called previous lattice. Each is defined by specific parameters like cell dimensions and internal angles. So crystal lattice structure is nothing but a unit cell which is repeated to form a crystal lattice. We have learned about common lattices and what are the Bravais lattices in this slide. Properties of crystalline solids. Crystalline solids have special properties such as anisotropy, sharp melting point, cleavage, and symmetry. Anisotropy. The physical properties like strength or conductivity vary depending on the direction within the crystal. Sharp melting point. They melt at precise temperature. Cleavage. They tend to split cleanly along the specific planes. Symmetry. Crystals often show rotational, mirror, and inversion symmetry. So these are the very special properties of crystalline solids. These properties are key in field from electronics to construction materials. Formation of crystalline solid. Crystals form through a multi-step process which is nucleation, growth, cooling rate, and speed crystals. Nucleation. They tiny regions where atoms start to organize into a pattern. Nucleation is nothing but organization of atoms in a pattern. Growth. These regions expand as more atoms join the structure. So when more atoms come and join a specific structure, this region starts to expand and grow. And then we have cooling rate. Slower cooling allows bigger structure to form. So when it cools slowly, bigger structures are formed. Seed crystal. Sometimes we introduce a tiny crystal to control and guide the growth for better uniformity. So crystals can be formed through multi-step processes which includes nucleation, growth, cooling rate and seed crystals. Understanding this process is critical for industries like semiconductor manufacturing and metrology. Types of crystalline solid. Crystalline solid can be classified based on the forces between the building blocks. These forces can be named as ionic crystals, covalent crystals, metallic crystals, and molecular crystals. So, wow, how can we define crystalline solids? Crystalline solids can be classified based on the forces between the building blocks. So, ionic crystal. What is an ionic crystal? Like NaCl, salt, high melting points but brittle. Covalent, like diamond, extremely hard, have high refractive index. Metallic crystals like copper, which are malleable, ductile, and excellent conductors. Molecular crystals such as ice, weaker bonds, low melting points, often held together by forces like hydrogen bonds. Defects. Point defects in crystal. No crystal is ever perfect, so that's important. Some common point defects include vacancies in interstitials, substantial impurities, and Frickle-Schottky defects. What are these defects? There are vacancies. There are missing atoms in a lattice affecting these properties. Interstitial. When an extra atom is positioned in an interstitial site, so extra atoms jammed into the space. Substantial impurities, such as foreign atoms replacing the original ones. And then we have Frenkel-Schottky defect, which is an defect in where ion displacement and vacancy pairs in ionic crystal happens. In ionic crystal, we also find Frenkel differences, which are ion displaced by normal site, and Schottky defects, which are vacancy pairs. These defects affect mechanical strength, conductivity, and even color of an crystal. So these defects are important to keep in mind and while researching more. Now we have defects, which are line and planar defects. Previously, we studied about point defects in crystal. Now it's about line and planar defect. Beyond point defects, there are line and planar defects, which is dislocations, grain boundaries, stacking faults, and twin boundaries. Dislocations, linear defects that allows material to deform, crucial for understanding material strength. Grain boundaries, where crystal of different orientation met. Stacking faults, layers in crystal stack incorrectly. Twin boundaries, two parts of crystal are mirror images across a boundary. These defects heavily influence the mechanical properties of metals and ceramics. Now, since we have learned the defects both in points and lines, we are going to jump into the next slide, which is about uh, determining structure X-ray diffraction. To study crystals, we use X-ray diffraction. Here, Bragg's law comes in. Bragg's law connects X-ray wavelength, atomic spacing, and diffraction angle, letting us see inside the crystal. There are two main types: powder diffraction and single crystal diffraction. What is powder diffraction? Useful for material made up of very small crystals. Single crystal diffraction gives detailed atomic level information. Each material produces a unique diffraction pattern like a fingerprint. Now we're going to learn about applications of crystalline solids in this slide. Crystalline solids are everywhere in our daily lives, from semiconductors to gemstones, metals, ceramics, pharmaceuticals. Semiconductors. Ultra pure crystalline silicon parts are used in computers and phones. Gemstones. Diamonds and rubbles owe their beauty to perfect crystal structures. Metals. Steel strength comes from its crystal structure. Ceramics. Insulates withstands extreme conditions. Pharmaceuticals. Crystalline drugs often have better stability and effectiveness. These applications just improve is just how important it is to control and understand crystallinity. We have almost come to the end of the slide, which is summary and conclusion. To wrap up, crystalline solids have very long range order, giving rise to unique properties like anisotropy, sharp melting points. We have sharp melting points, cleavage, and symmetry. They form through various multi-step processes, which includes nucleation, growth, cooling rates, heat crystals, effects. Whether it is a point, line, or planar, are critical for understanding the material behavior. So we learned about the defects, which was point defects and line and planar defect. Point defects includes vacancies, interstitial, substantial impurities. It also includes Freckel defects and Schottky defects. And for defects in line and planar, it has dislocations, grain boundaries, stacking, twin boundaries. Finally, for semiconductors to gemstones, applications of crystalline solid power much of modern technology. We learned about the applications, which includes semiconductors, gemstones, metals, ceramics, and pharmaceutical. And we determine a crystalline structure using X-ray diffraction. Uh, This is where Bragg's law comes in, which shows the powder diffraction, and there is another diffraction called a single crystal diffraction. And then we have how our crystal structure lattices are formed. It is formed using a unit cell, which is the smallest repeating unit of this lattice. By repeating a unit cell, the full crystal structure is built. And then what are the different types of lattices? It includes simple cubic, body-centered cubic, face-centered cubic, and hexagonal. Thank you. Thank you so much for your attention. I hope you appreciate how crystalline structures are quite shape the world around us.